Hi and hello everyone. What we will see next is what are called as priority queues, right? You know, these kind of systems occur very frequently or very often you would see in real life systems, right? So, this is also models which have been studied long back. What we are going to see is that we are going to see this queue in the Markovian framework, though it might be sometimes easier to get the required performance measures using a more general approach, but we will be viewing it from the Markovian perspective. Recall that what we have considered so far are all birth-death queuing systems and Markovian queuing systems, but they all have queue discipline as first come first serve or first in first out models, right. So, the customers were selected for service on a first come first serve basis or first in first out basis, right. But there do exist, as you know, alternative queuing disciplines which include last come first serve like in an inventory system, or selection in random order or priority, etc. But we may not see all, but what we are going to look at is this particular queue discipline is what we are going to look at it. Okay. So, in priority schemes, when in priority queuing discipline, when priority is being employed, the higher priorities are selected for service ahead of those with lower priorities. Okay. This is done in two ways. One is with preemption and without preemption. And what is that? So, in a preemptive case, the customer with a higher priority gets into either gets into service immediately on arrival if no customers are there, or if a lower priority customer is getting service. Okay. If the customer who is currently getting service is of the same priority or higher priority, obviously he will get into queue. He will interrupt any service that is ongoing for any lower priority customer to start his or her service, is what the preemptive case, because he preempts or interrupts the service of any lower priority customer that might be ongoing, right, to start his service. Otherwise, he will get into the queue. Okay. Now, depending upon what happens to the customer whose service has been interrupted in the middle by a higher priority customer, this could further be divided into two cases. One is called preemptive resume. In this particular case, the service can be resumed from the point of interruption, right. So, that is one case, or it can be started afresh, right. So, you could have things like situations in both may be possible here, because it is some sort of paperwork kind of thing that is being done as a service. Then wherever you stopped, probably you will start from there for the lower priority customer. That is one way. If it is something which requires some startup things, and then say for example, if you are looking at some kind of heating processes involved, then you have to start afresh because the already done one is not of no use kind of thing, right. So, that could be preemptive non-resume. So, in general this could be of course, you could think of more general situations as well. This is preemptive case. Preemptive case means he preempts any ongoing service of a lower priority customer. That is the case. In non-preemptive case, the higher priority customer goes into the queue, but either if you have a system where separate queues are there, of course he will join the queue of the appropriate one, but for the system as a whole we might consider this a single queue, but then where he will move ahead of any lower priority customer, right, but he will be behind any higher priority customer or of the same level priority. The ones who arrived before him will be ahead of him, right. So, that is how within that priority, of course, they may follow an FCFS basis in that case, right. So, even if there is a lower priority customer is getting service, he will not preempt the ongoing service. So, he is not going to disrupt any ongoing service that is being given to a lower priority customer. He will just wait, and then, but he will move ahead of any of those lower priority customers in the queue when selection for service is coming, right. But must wait for any customer, whoever is there, whether higher or lower, currently ongoing service he is not going to interrupt. That is what we said, irrespective of priority, any customer service to complete the service he will wait. So, that is the non-preemptive case. Okay. And it is convention to use the lower numbers to denote the higher priorities. So, we may use 1 for the highest priority and 2 second highest, 3 the third highest, and so on. In case of 2 priority, like we might use simply 1 and 2, where this 1 could also be referred as higher priorities and 2 would be referred to as lower priorities, higher and lower. Since there are only 2, so you could also call this for convenience that you have seen. Now, these priority queues, because of this priority discipline that you have here, are in general difficult to analyze compared to the non-priority case. But if you recall that for the MM1 queue, for example, and some other related models or anywhere, the derivation of the steady state system size probabilities did not depend on the queue discipline. We pointed out this while discussing MM1 also, and at which point the queue discipline comes into picture also we have discussed at that point of time. So, that is what you may recall, and it can be shown that indeed, like it can be shown that as long as the selection of customers for service is independent of the relative size of the service time, PNs would be independent of the queue discipline. What does that mean? That would mean that, for example, if you are looking at a situation where the shorter service time requirements are taken up first for service, so those kind of things is not happening. That is the case where the selection would depend on the relative size of the service time. Shortest service time first, right. This is the one queuing discipline that is existing, and we may not see that, but of course that is one such discipline. So, in such case this is not the case. As long as such situations are not there, the selection of customers for service is independent of the relative size of the service time, then PNs are independent of the queue discipline. As long as this is true, you know that the Little's formula remains unchanged, and hence the average number in the system, and hence the average waiting time, right. But we know there will be changes in the waiting time distribution. Again, you may recall our MM1 analysis where we said that the first come first serve is what we are assuming while deriving the waiting time distributions. If not, what would happen? You can imagine in that situation. Okay. So that's what you can see, and we can now make a claim which says that waiting times are stochastically smallest under FCFS with all other things being equal, and introduction of any scheme of priorities which does not depend on the service time makes the higher order moments worse than what was it under the FCFS discipline. That is what we mean. So, higher order moments under this is stochastically smaller, right, and it will be better under FCFS scheme. That is what we are meaning, which means that you will have a scenario where the FCFS scheme produces a lower variance for the waiting times under FCFS scheme than any other scheme. Okay. And what does that lower variance would mean? As you know, for any data, mean and variance are important. Mean gives the what is the center point of the data, and the spread or the dispersion is given by the variance. Now, variance smaller means the points are more closely clustered around the mean, right. That is the meaning of lower variance. So, In this case, that there is a greater equality among the waiting times of various customers. That is what it would mean, because any customer that you pick it up, it will be, they will have more closer waiting time durations, there is no undue wait. So, in that case, this could also be, lower variance can also be associated with in some sense the fairness of the system, right, because it is fair to everyone, so that almost everyone gets almost equal waiting time, rather than someone getting 5 time units, someone getting 20 time units, and if you someone getting 10 units, someone getting 13 units. So, this is which is more reasonable is what then you are thinking. So, this is what is, you can think of this, or you can view it as if it is a more fair scheme, the FCFS scheme, than the other scheme, right. So, that is the implication when you look at variance as a measure of fairness in a way. So, the lower variance would give you more fairer waiting times for all the customers. Now, this claim is very difficult to prove at this point with all the materials that we have at hand, or even we are going to see later on also including that. So, you will need, because you need to know what do you mean by random variables being stochastically smaller and so on, and so many other results connected with that. But we can get an idea about why this is true or how this is true, right. If we was just taking an illustration. Okay. So, let us look at this diagram that we have put here, which depicts the arrivals and departures under the FCFS scheme, and the y axis denotes the number in the system, and this is the timeline, and at time 0 it starts with 0, and at time 2, which is t1 equal to 2, the first customer arrives. The orange ones are depicting the arrivals, and the blue arrows would depict the departures. The customer numbers with different colored are boxed here, which is corresponding to the arrivals and their departures point, right. And the time at which the events are happening is basically denoted, written here down the line. Okay. Suppose our customer 1 comes at time 1, at which point the system size becomes 1, okay, and his service started, and then his service will be continuing, and at this point T2 equal to 6, the second customer comes, but the customer is getting served here. So, the system size becomes 2, and then at the time T3 equal to 12, the first customer finishes his service. So, the second customer gets into service and the system size becomes 1, and at the time 14, then third customer comes. So, system size becomes 2, but the second customer is getting served here, and this T5 18, the fourth customer also comes in, but the second customer is still in service. So, system size becomes 3 here, and at time 20 the second customer leaves. So, the system size becomes 2. Okay. Now, there are 2 customers, but since FCFS, the third customer is picked up for the service, and his service is continued from 20 up to 24, and at this point the third customer service ends, and then system size becomes 1, and his service starts at 24 and ends at 28. So, the system becomes 0 and so on. So, this is a typical sample path, right, what we call it as sample path for the system size in a single server system, right. Now, under FCFS, now what are the waiting times, if you think waiting times in the system, but that is what we are looking at it. First customer arrived at this point, which is 2, and he left at this point 12. So, his waiting time is 10. Second customer, it is 6 and 20, it is 14. Third customer, it is 14 and 24, it is 10, and the fourth customer is 18 and 28, it is 10. So, the mean is 11, and the unbiased variance, which means the sample variance, right, unbiased sample variance is 4 here, right. That is what you can compute it under FCFS. Now, if you look at what is happening under the last come first serve discipline, suppose if this is the discipline, it is very easier to see. Of course, first 2 customers behavior would not change, but at the end, at this point, when 2 customers are there, right, when the 2 customers are there, the last come first serve discipline if you are employing, then the fourth customer is picked up for the service, and the third service time, I mean irrespective of the customer, you have picked the fourth customer, but he will again have 4 units. So, his service will end here, right, his service will end here, and this is the service duration of the fourth one. So, basically what you will have here, instead of 3 you will have 4, and in this place 4 he will have 3. So, the fourth customer would exit here, and the third customer would exit the system here. These things would remain the same, only in these 2 points these 2 would get interchanged, and that would change, right. If the fourth customer is here, he arrived at 18, and if he leaves at 24, his waiting time is 6. Third customer, he would arrive at 14 and he would go at 28. So, his waiting time is in the system was 14. So, these are the 4 waiting times of these 4 customers, which still has mean as 11. It is not going to change that, but the variance now if you look at it, it is 14.67 as compared to 4, which is much larger than the FCFS scheme. So, variance is higher under FCFS scheme, and this is what the claim typically is what we made. It is basically the claim is in terms of the distributions you are talking about, but that would imply that it will have higher order moments worse under in this any LCFS or priority schemes than it was under FCFS. That is what it would mean, and that means that it becomes in some sort of unfairness system. But there is always a question about fairness in the system and the Q discipline. This is always in conflicting nature. So, if you want to introduce this, then basically you are compromising on the fairness of all customers. But if it has to be for certain reason, that if you have to create a system where this particular group has to be given priority, you have to live with that unfairness in that situation, right. That is what it will turn out to be. Furthermore, in further extension of the ideas that we are already seeing it, right. So, one can also show that see that the remaining total service or work required for a single server at any point during an arbitrary busy period is independent of the order of service, meaning that any priority that you introduced or last come first serve you introduce anything, this will be independent, the work required for a single server at any point of time will be independent as long as what we say the system is conservative. What do we mean? It means that no system needs are created or destroyed within system, right. Whatever it comes, for example, there is no reneging happens in the middle of the service. So, that means the system need is getting destroyed for the remaining period, and the one customer also is lost. Now, how do you count whether this is served or not served is also another question, right. But his needs are destroyed, right. So, this destroyed, or you might look at the case where again when in priority, when the preemption happens, right, what happens to the preempted service which starts all over, then again some portion which server has already put in, that is getting destroyed, that service needs have been destroyed, right. And when you start afresh, then you are creating additional need as well, right. And also like when there are customer, you are not forcing the service to be server to be idle is not the situation. So, if you do not have any such behavior, then that system is what is generally called as a conservative systems. So, in such conservative systems, the workload for the server is independent of any order of service. So, that is also one can see. Okay. Now, what we do next is we will start with a priority queuing system, and of course, we will, as I said, that this is a Markovian system that we are thinking about, and in that framework we are going to look at that. So, customers would arrive as a Poisson process to a single exponential channel. You can think of, and this is the non-preemptive priority system with 2 classes is what we are going to consider. So, you can think of as if it is a typical MM1 system only, right. but with certain changes. The changes are, a customer upon his arrival is assigned one of the two priority classes. Okay, arbitrarily you can think that it is independent of everything else, that any particular customer can be assigned with certain probability class 1 and certain probability class 2. You think it that way, that would be equivalent to, then the first or higher priority customers arrive as a Poisson process with rate lambda 1, and the lower priority customers arrive as Poisson process with rate lambda 2. The total arrival rate would be lambda. So, that is the Poisson process with arrival with rate lambda, with arrival rate lambda, which will be then equal to lambda 1 by lambda 1 plus lambda 2, and the probability of that assignment, if you are looking at this, then it will be lambda 1 by lambda is the corresponding probability, you can think. Okay. And we also assume that there is no preemption takes place. So, this is non-preemptive priority system. So, there are two priority classes, higher priority one arrives at the rate lambda 1, the lower priority arrives at the rate lambda 2. Now, such a system, it can be modeled with the assumption of exponential service and the arrival process being Poisson, right. The arrival could be with certain probability at any given point of time, the arrival could be higher priority, and with the remaining probability the arrival could be of the lower priority. Okay. And every other assumptions connected with such a Markovian system is in place, then the system can be modeled by a continuous time Markov chain with state space as this. Okay. So, 0 we denote it that system is empty, there is nothing on that, and a triplet to denote M, N, R. And what is this M? This M denotes the number of priority 1 customers or higher priority customers. This N is number of lower priority customers, and R is the priority of the customer that is undergoing service at the current time, is what is denoted by R. So, this M and N both cannot be 0. If both are 0, then it boils down to this particular state, and there is no customer, nothing in the priority. So, that is why that is denoted as separate state. This M and N both cannot be equal to 0. So, that is what we write it as maximum of this M and N is strictly greater than 0. So, or at least 1, whereas M and N can take 0, 1, 2 and so on, and R is either 1 or 2 depending upon whether the customer who is currently in service is priority 1 or priority 2. Okay. And the corresponding steady state probabilities with both M and N not both being 0 at the same time are denoted by P suffix M, N, R. So, the first suffix is number of priority 1 customers, the second suffix is number of priority 2 customers, and R is the customer is in service is of priority R, where R is either 1 or 2, and P naught is the system being empty, and L, LQ, W, Q, W with superscript within bracket I would denote the corresponding measures for the corresponding priority class. If it is 1, it is higher priority, if I is equal to 2, then it is for the lower priority in these two priority cases, right. So, this is a general setup here, right. Now, we will assume, we will consider 3 models and we will compare to make certain inferences. So, the model A would be equal service rates, meaning that both the class demand an equal service need from the server. That is, the service rate, service distribution is exponential, we already mentioned, right. But the service rate or the mean service time that is required to serve either priority 1 or priority 2, they are equal to the rate mu, we call it. Okay. Then we defined rho 1 equal to lambda 1 by mu and rho 2 as lambda 2 by mu, and rho as rho 1 plus rho 2, which is again lambda 1 plus lambda 2 by mu, and that is lambda by mu, and we will assume that rho less than 1 for the stability of the system, for the underlying Markov chain to be positive recurrent and so on. right. So, all these lambda 1, lambda 2, mu, of course, we assume to be strictly greater than 0. So, rho less than 1 is what is the stability condition that is required for this steady state to exist. Okay. Now, once we have this one, right, as the state space, now we can write the balance equations of corresponding to the different states in the state space, right. The generic ones are what we are calling it as equation A and equation B, which correspond to a general state of m strictly greater than or equal to 1 and n is greater than or equal to 2 and m greater than or equal to 2, n greater than or equal to 1. This is the general one. Okay. That means mn with respect to 2 and mn with respect to 1 mean the current service currently being rendered to which priority customer is what denoted by this third subscript as we already denoted. So, this is the equation and this is the once we have this equation which is the general one, then one has to look at the boundary cases. Say for example, n is greater than or equal to 2. So, what will happen if n is equal to 1 is what will come here, right. m1 2 which can be right deduced from this by looking at the boundary. This is 1 n 1, okay. At 0 n 2 and there will be some changes will be there, you cannot directly deduce from here, right. Remember, we will come to this how do we get to this, but once you know this, then certain things like you can deduce from here looking as a boundary, but in boundary the behavior might be slightly different and you have to account for it. Say for example, this 1 n 1, 0 n 2, m 0 1. So, these are all 0, 1 and this is specific to these particular states 0, 1, 2. There is one customer in the service and which is a priority 2 and there is one customer in the service which is a priority 1. In that case, like how this behaves, okay. So, you need to carefully look at and write down these portions, but once you understand the genesis by looking at these two, what are the possibilities that can lead to this particular state. So, this is the general principle in the balance equation writing with respect to any Markovian model. So, we are getting practiced with many such things, right. So, this is m and 2. Suppose if I look at this equation A first, okay, what we are writing is this one, okay, what we are writing is this one, okay. So, now look at the equation A case which is m n 2. This we are looking at, so we are depicting only for the state m n 2 what are the possibilities, what are the rates or in which way the process or the CTMC can move out of the states or from where it can come into the states to write down the balance equation, right. Now, what might have come? Remember this m and n, the condition under which m is at least 1, n is at least 2 is what is, that is what we are writing it generically, okay. Now, what can happen while it is in this particular state, okay. An arrival can happen which is of priority 1, an arrival can happen which is of priority 2, right, or currently undergoing service is of priority 2. So, a service completion can happen, okay. These are the three possibilities that it can happen, right. Now, with what are the rates for these three possibilities and to which state the process will move at the end of that transition is what we have to look at it, right. So, currently m and 2 with a rate lambda 1, an arrival of priority 1 customer, this will move to state m plus 1 n 2, right. So, when you say m and 2, this one customer from this n is in service, that is what you have to remember, right. With an arrival we will take it to m plus 1 n 2, or if there is an arrival of the priority 2 customer that can happen with rate lambda 2, this can go to m n plus 1 2 going out to m n plus 1 2 it can go, or if the service completion happens, right? If the service completion happens with in this case, right? So, current customer is being served is of priority 2 is a non-preemptive. So, that is why this whenever this arrival happens, it just pushes to m plus 1 n 2, it is non-preemptive. If it is preemptive, of course, this will remain in n and then this will become 1, that kind of thing can happen, right. That is what you have to remember. Okay. Now, m and 2, if the service completion happens, then this the priority 2 customers would be reduced, but since there is at least one priority 1 customer in service, so that will get into the service. So, the state movement would be with rate mu, this will be m n minus 1 and 1. Okay. So, this green color one I have depicted it for the states with the third suffix as 2, and this blue colored one is with the third suffix being 1, which means based upon the current service. And if you can see, you see that it's impossible to depict the whole thing because this is in 3 dimension you have to depict. Okay. So, it's impossible to do that. So, that is why we are specific cases we are looking at it. So, the total rate of outgoing transitions is basically lambda 1 plus lambda 2 plus mu, and that is precisely what we are writing it here. Lambda 1 plus lambda is basically lambda 1 plus lambda 2, right. Lambda 1 plus lambda 2 plus mu from the state m and 2, it is clear, right. Now, from which way it can come to state this state m and 2? It could have been m n minus 1 2 and with an arrival of lambda 2, arrival rate of lambda 2, which is arrival of lower priority customer, it can move to m and 2, right. Or it was in state m minus 1 n 2 and with an arrival of priority 1 customer, with an arrival of higher priority customer, this can move to m and 2, right. These are the only two possibilities. Through any service completion, it cannot come to this when m is strictly greater than or equal to 1, right. That is what is happen. So, basically lambda 1 corresponding with from this state and lambda 2 from this state is can only way it can come to state m and 2. So, that shows how we have written this particular equation, right. So, try to understand this, fine. This is about the first equation, which is equation A. Now, let us look at equation B, right. In which way this can go out? It will have almost similar way, right. So, in m and 1 is what we are looking at the state. From this, an arrival of priority 1 would make it to m plus 1 n 1, and arrival of priority 2 would make it to m n plus 1 1, and a service completion of this, right, would make it to m minus 1 n 1, because now since m is at least in this particular case m is at least 2. So, there is at least one more customer is there here. So, this will be at least one would be there. So, his service will start. So, it will be in the same priority customer, same priority level, because already there is at least one priority 1 customer is waiting. So, his service will start. So, basically from m and 1 with a service completion it will move to m minus 1 n 1. So, the total rate of going out of the state is lambda 1 plus lambda 2 plus mu, but where it is moving is what you need to understand, right. So, that again lambda 1 plus lambda 2 plus mu times p m n 1, that is clear. Now, what is the flow into the state, right. The flow into the state, it can be from m minus 1 n 1 and an arrival could happen of priority 1 with rate lambda 1 to make it come to the state m n 1, or it was m n minus 1 1 and an arrival of lower priority would make it to come to state m n 1, right. Or here we said that it goes out to something here, this is what is coming in here, that one. It could have been in m n plus 1 2, right? Again, n is at least greater than or equal to 1, m is at least greater than or equal to 2 case is what we are looking at it. M n plus 1 2, and at the service completion of the lower priority customer, it will move to m n 1. Now, this 1 means that one of this m customer is what is getting service now, right. So, from here it went to this row. Suppose if you think of this as two different layers, one mn 1 is somewhere down and mn 2 is somewhere up, then mn 2 to mn 1, this is what is coming down and this is what is coming down to this particular case here, right. So, this is for the second equation, which is equation B, right. You can understand lambda 1 m minus 1 n 1, and from m n minus 1 with rate lambda to r mu, there are two mu's actually you have to look at here. So, one is this, the other is this, right. Now, if there is m plus 1 n 1, right, m plus 1 n 1, a service completion would again bring it back to m n 1. So, there are two, one mu is from here, the other mu is from here. So, there is mu from m plus 1 n 1 and m n plus 1 2, this will come to state m n 1. So, that is what this equation is. So, understanding this is what is the essence of any Markovian model that you will see in any CTMC, and more so in queuing that you have to write down this. If you consider a Markovian system, it all boils down to writing down this balance equation. This comes with practice only, right. It is not going to come in one or two models, but we are telling the principles in which by which you can arrive at these equations. You just have to look at all possibilities that can happen when you are writing down the flow balance equations. The flow into the state and flow out of the state is what will give you this balance equation. Now, if you sum both sides, then the left side would be equal to the right side. So, the difference would be equal to 0 is what then you would see here. Similarly, the other ones, some of them can be easily written down as a balanced as a boundary states. Some of them, even the boundary state, the behavior might be slightly different. So, you need to worry about it that, okay, for example, in this 0 and 2 case especially, when there is 0 priority 1 customer, if there is n here, it will not follow from here as such, because there will be a mu here, it will come because there is no customer of priority 1 available. So, it will start serving the priority 2 customer. So, that is why this term will come into the picture, right. So, these are certain modifications which you will know, but you can work on the same principle to arrive at these equations, right. This is the balance equations, and how we have obtained is what we have explained through these two diagrams. Now, by Little's law, which you apply to the server now, right, you can see that rho is the fraction of the time the server is busy, or 1 minus rho is the fraction of the time the server is free, and that would be equal to P naught, which is equal to 1 minus rho, right. You can write that. Similarly, the fraction of time the server is busy with a priority R customer is rho R. So, that would mean summing over this P m n 1 with appropriate mn's to get this rho 1, right. So, this m is equal to 1 to infinity of for all possible n's. If you sum, you will get rho 1, and with n is equal to 1 to infinity with all possible m's, if you sum, you over get this rho 2. So, from this Pm1, Pm2, if you get, you will get this relationship, this is true and this is also true, and P naught is 1 minus rho, which is 1 minus of rho 1 minus rho 2, 1 minus rho 1 minus rho 2 is what then you are getting here, that is P naught here. Now, since here the exponential service time with the same rate is there for both the priority classes, the system size steady state distribution for the number of customers, if you think, right, if you think n as the number of customers, that can happen in many different ways depending upon how many number of priority 1 and priority 2 customers are there, but their sum should be equal to n, right. That is what you would see, right. If you sum these two, right. So, if you sum these two for n greater than or equal to 1 only we are writing, right, because P naught is 1 minus given here. So, sum is has to be at least n. That means if there are n minus m priority 1, there must be m priority 2, so the total sum is n, where this m can range from 0 to n minus 1, and this could also happen in this way with respect to mn 2, mn 1, both you have to sum. So, this total sum, if you take this particular possibilities, then this Pn would be given by this. So, this is another thing that you can also notice from. So, if I want this, if I compute this explicitly, then I can compute this sum and this sum to get to this, but even otherwise, one can easily see that this is what is going to happen. We know all these things that if you have this will all be satisfying this, but obtaining this Pmn1 and Pmn2 or Pmnr in general is very difficult here. Okay. So, what we will try to do is we will try to obtain certain expected value measures using generating functions, which is what typically done in such complex models. At least the expected value measures you can obtain it explicitly, so that you can do the performance analysis of that. Okay. For which what we do, we define, because of this 3-dimensional nature of the process, because basically this CTMC is of 3 dimension, and because of this 3-dimensional nature, like we have to have more complex generating functions, but because the third dimension is either 1 or 2, so you can slightly make it in 2 dimension in the following way. First you define Pm1 of z, right. So, Pmn1 z to the power n is what you are looking at here to get this quantity, which is basically for a fixed value of m and the current and the third index, which is being 1, you are denoting its generating function with respect to this n. Similarly, m2 is same thing, but now with respect to 2 here, this is Pm2. Now, plug it this Pm1 inside, put another index y to the power m for this index as well, for m is equal to 1 to infinity, and call this as h1 of yz. Now, h1 of 1 will give you rho 1 as per our this observation, right, as per this observation. h1 1 when you put both z and y as 1, it will give you rho 1, and h2 is basically with respect to the priority 2. This is, you can think of it something like a partial generating function with respect to the priority 1 customer in service corresponding to all those states. This is corresponding to priority 2 customer in service corresponding to all those states, okay, if you expand it in that form. So, h2 of 1 will be equal to rho 2, and this is what will give you my h2 of yz. Now, if I sum these two along with P naught, I am going to get the full generating function, which is the joint generating function for the 2 classes regardless of which type is in service, right. This is partial generating function depending upon which type is in service. So, this is a full generating function. If you write it explicitly, this is what you are going to get here, right. This is what, remember, like m is equal to 0 to infinity, n is equal to 1 to infinity, here m is 1 to infinity, n is equal to, so all these things, this indexes you need to little bit carefully write down, that is all. So, then you will get this, you will get these, this is an alternative way of writing down for some time to be helpful to do that, okay. So, this is what you get as the joint generating function. You have this partial generating function, you have like the first step generating function of in 1 dimensional case. Now, note that when you put both y is equal to z here, this will boils down to generating function of an and q, and because what does it mean, that no priority distinction is being made, right. So, you can observe from here there is no priority distinction is being made. So, your hyy will be p naught by 1 minus rho y with h11 equal to 1, that is one observation you can make. And also, if I take this full generating function, differentiate with respect to y alone and substitute and evaluate it the derivative, this partial derivative at y is equal to z equal to 1, what you are going to end up with is L1, okay, which will be equal to LQ of 1 plus rho 1, right, and plus rho 1, right, and this is equal to lambda 1 times W1. So, from once you obtain this quantity, then you can obtain these quantities and WQ as well from LQ using the Little's law. Similarly, if I differentiate this generating function partially with respect to z and evaluate it at y is equal to z equal to 1, I will get L2, and from which I can get the other performance measures. So, basically since we are interested in these 4 performance measures, that is what would be our interest as well. Now, how do we get that? You have to go back to the balance equation here. You multiply. So, each equation with respect to y to the power m, z to the power n with appropriate m and n here, and sum everything to arrive at this expression for the h1 and this expression for the h2 partially, if you look at it. Okay, this is a task that you need to execute to see that exactly you arrive at this expression by the appropriate powers of y and z, and summing over that you will end up with these 2 equations. But now if I look at these 2 equations, there are 3 unknown things which are there here. One is P11Z, P02Z and P0, right. In both the equations you have this. So, if you want to determine this little bit more completely, so we need if you want to know completely, then you need the values of these 3. But one can find a relationship between these 3 quantities as this by using the equations corresponding to P0N2. P0N2, that equation, the equation corresponding to this you can use by summing z to the power n from 2 to 2 onwards, and then arrive at this expression here. Now, what we have done is P11 you have obtained in terms of P02 of z and P0. So, if you substitute this here P11 in place of P11 this expression, you can get a simplified version for H1 and H2, which will be now in terms of P0 and P02x. Okay. So, which P0, P02x, and once you know H1 and H2 and P0 if you have, then you can get this HYZ, which is equal to this expression, which is in terms of P02x and P0. So, there are 2 terms here, one with P0 and certain coefficient of that. The second is P02 with this coefficient here, P02 of Z generating function. This is a quantity, this generating function. Now, from this fact H11 equal to 1, we can obtain P02 of 1 as rho 2 by 1 plus rho 1, okay, P02 1. Now, why we need here? If you want to determine L1 by taking the partial derivative of this with respect to y and evaluate it at y is equal to z equal to 1, here the exact evaluation is not possible because it will be 0 by 0 form you will get. So, you will take it as a limit in the limit form. So, when you do that, you will get an expression which would require not the complete functional form of P02 of z, but P02 of 1 only you need, but that P02 of 1 you can explicitly get using this condition, and P0 anyway you know it is 1 minus rho. So, everything can be determined completely to get this L1. Now, once you have this L1, right, once you have this L1 or L2, whatever is the case. So, L1 suppose if you have, now L2 you need to determine, but for which you make this use of this observation that the total number of customers in the system is the same as an MM1 system. Since that is the case, L1 plus L2 would be equal to the corresponding value for the number in the system of an MM1Q, which is rho by 1 minus rho. So, using this one can obtain directly through the partial derivative of this generating function, but it is much easier that use this relationship because you already know L1. So, L2 you can obtain it from this relationship as L2 equal to rho by 1 minus rho minus L1, and once you know L1 and L2, the other measures LQ and WQ and Ws, right, with respect to each of these priority classes can be obtained through this relationship that we have here. Now, we will not mention that result, but we are mentioning the final results for certain purpose of comparison. So, we will take LQ with respect to class 1 and class 2 and completely. For LQ completely is rho square by 1 minus rho, because that is what you are going to get for an MM1 model. Now, LQ1 is obtained to be this and LQ2 is obtained to be this from this relationship. Now, how do we obtain here? You have to obtain from L1. To obtain L1, you have to differentiate this derivative, this generative function with respect to y, and evaluate it at z equal to y is equal to z equal to 1 as y and z tends to 1, the limiting case. Then you will arrive at L1 and from there you get this. So, this is, we are putting it in a boxed environment because we want to refer to this at a later stage for some observation that we want to make or for some comparison that we want to make. Now, this portion is extra for those of you who are interested alone. Of course, otherwise do not bother about this portion, that this is extra for interested. You can refer to Miller 1981 work to see that the actual probabilities for priority 1 customers can be shown to be obtained as this. Okay, that is anyway extra, do not worry about that. Now, with this mean value results, we have obtained what? Not steady state probabilities, but certain mean value results. With this mean value results, we can make some observations here, which is of important, though we do not have the complete distributions. Okay. The first part is that lower priority customers always wait on an average longer than the higher priority customers, right, intuitively, but it can also be shown to be, right, you take the expression of WQ2 which is equal to this, which can be written as this form, which can be written into this, where this is WQ1, so which is greater than or equal to this whenever rho is less than 1, okay, that is the condition for stability. But however, this is not always true. WQ2 is strictly greater than WQ1, but LQ2 is not strictly greater than LQ1, meaning the waiting time for the average waiting time for the lower priority customers is longer, but the number in the system need not be so. Number in the system for the lower priority customers may not be longer than this particular case. You can show with certain parameter values picking lambda 1, lambda 2 and mu, you can show that this greater than LQ1 and this quantity is less than LQ1, both are possible, right. So, that is an exercise problem in the text, but of course, that is one can make an observation here. Okay. Now, the second observation is that as rho tends to 1, your LQ2 tends to infinity, and so does the all other quantities connected with the lower priority customer. Okay. However, as long as your lambda 1 by mu is less than 1 is held constant, right, LQ1 would approach a finite limit, meaning, right, you may think that how you are going to keep this as a constant, because by adjusting the rate lambda, because when this is can happen, so that it can happen as rho tends to 1, can happen with lambda 2 tending to infinity in some sense, that alone can happen, or if mu happens, then accordingly lambda 1 need to be adjusted to keep this as a constant. In whichever way it is, if this is held constant, then this will approach a finite limit. Means that the first priority means go to infinity only when this tends to 1. Okay. Now, what does it mean is that it is possible that the higher priority customers do not accumulate even when the overall system state does not exist, means the overall system size is exploding. Even then, it is possible that you have a system where the higher priority customers do not accumulate. They exhibit in some sense a steady state behavior or stable behavior. Okay. Now, the presence of class 2 customers still creates delays for class 1 customers, even though they have priority. That is because of this non-preemptiveness. That is, one can show that LQ1 when lambda equal to 0 is smaller than LQ1 when lambda strictly greater than 0. Okay. But as you know, if it has a preemption, if it is there, then the priority 1 would be a sort of an MM1Q type, it will behave, because it will preempt any of this. Then the class 2 customers do not affect, but as long as the non-preemptiveness is there, then the class 2 customers does affect class 1 customers behavior or priority or the waiting times. Okay. So, the average number in the Q is the same as an MM1Q. Similarly, the unconditional average weight, meaning the weighted waiting times of these two weighted by this lambda 1 by lambda and lambda 2 by lambda is also same as an MMQ. These are some observations that you can make with respect to this non-preemptive priority queuing system with two classes of customers, which is what we with equal rates, which is what is model A that we have considered. We have written down the balance equations. We have cannot solve completely, it is very difficult. So, what we did is expected value measures that we have obtained, which we have given it in the boxed one, which we are going to refer back to in the later lecture because of some comparison that we want to make. Okay. So, of course, we will end here and we will continue this same priority queues further discussion on this model in the next lecture. Thank you. Bye.